Hello, today we are talking about our test for convergence at endpoints. So this is the handout that you're looking for. We did many of these tests in class, so we're actually going to jump to the direct comparison test. If you look at the bottom of the page, it says 410, and the top of the page looks like this. So again, we're on the direct comparison test. So what I'd like you to do right now is I would like for you to read the direct comparison test up until my red squiggly line. So please pause the video here and read that part. So basically what this means, if we know that the nth term of C is bigger, it's always, whatever that value is always going to be bigger than the nth term of the series we're talking about. If we know that C converges, that means automatically that A converges. And that's because A is larger. If C is larger. If C is always larger and it converges, we don't have a choice but know that A must also converge as well. So below the red squiggly line means, okay, the exact opposite. If D is smaller, okay, D sub n is smaller than A, that means if D diverges, that means automatically A has to diverge because each of those terms is larger than each of the terms in D. So, given a series bounded below by a series that is known to diverge. So please read the next thing. Okay, so examples 7, A, B, and C. So starting with A. Determine whether each series converges or diverges. So we're going to use our direct comparison test. Basically, I need to find something to compare natural log of n over n to. So I'm going to look for something that I recognize and I know, and I kind of see a harmonic series in there. So I'm going to compare that to just 1 over n. So is natural log of n over n going to be bigger than or smaller than 1 over n? And natural log of n is going to be a value 2, 4, 8, 12. So that's going to be larger always than 1 over n. So natural log of n over n is larger than 1 over n. But what do we know about the series of 1 over n? Well, this is a harmonic. You can also talk about this being a p-series where p is greater than or equal to 1. And so the harmonic series diverges, which means, therefore, by direct comparison, this sum for natural log of n over n must diverge also. And that's because it was larger than the one I was comparing it to. So if you need time to write that down, pause the video here. Okay, B. Now we have this square root of n over n squared plus 1. This one is sort of tough to decide what to compare it to. But what you want to look for is basically what's the exponent going to be of this thing. So when I break this down, I really have an n to the 1/2. I don't care about the constants because as x goes to infinity, my constants become negligible. They don't really matter. I hate to say that about the poor little constants, that they don't really matter, but they don't really matter. So if I just look at the big players of this is n to the 1/2 and this is an n squared. And that's the same as n to the 1/2 minus 2, which is n to the negative 1 1/2, which is n to the negative 3/2, which is 1 over n to the 3/2. So that's what I want to compare it to. So once I know what I want to compare it to, I need to know, well, which one's going to be bigger. So is n, the square root of n over n squared plus 1 going to be bigger than or smaller than 1 over basically the square root of n cubed? So which one of those is going to be larger? Because I'm taking the square root of n cubed, that thing has a smaller exponent. That thing is going to be larger. So this is going to be larger. If you need time to kind of process that, pause the video here and put some n values in. Just keep plugging some n values in that are helpful and see that the 1 over the square root of n cubed is larger. So now I need to know, well, do I know anything about this term? I mean, this series. And I do. So this sum, n is equal to 1 to infinity of 1 over n to the 3 halves, is a p-series. And this is a p-series, and p is greater than or equal to 1, which means we have a convergence. So my p-series converges. Now, if I know a larger series converges, that means the smaller series must also converge. Therefore, by the direct comparison test, the sum I care about, which is the square root of n over n squared plus 1, must also converges. So the things I have to see, this therefore statement I have in red, I also have to have this thing in red, and I have to have what I have also written in red. All of those must be shown for the direct comparison test. So now we're looking at example 3. No, sorry, limit comparison test. I'm on the wrong page. Sorry about that. Okay, limit comparison test. So will you please pause the video here and read the limit comparison test? Okay, so that's a lot of information, and unfortunately, yes, you need to memorize this one. And again, we've kind of done them in order. This is probably your last resort because it is so much work, unless it's one that's going to simplify quickly and easily. So let's look at part A. I need to figure out what am I going to use as A and what am I going to use as B. And what I want is start with the first one. So we have, this is a sub n, which is 2n plus 1 over n plus 1 quantity squared. So I need to pick something to compare this to, and I need to know whether this thing I'm comparing it to converges or diverges. Okay, so first of all, I know I'm just going to go ahead and pick one that I like. And again, we're just picking one that we like. It may not be a conclusive test. I'm going to choose 1 over n. 1 over n is easy. I know that this sum diverges. Next thing I need to show. I need to show that both of these things are greater than 0. So I need to say 2n plus 1 over n plus 1 quantity squared. That's going to be greater than 0 as long as I start with n is 1. That will always be greater than 0. And 1 over n will be greater than 0 as long as I start with n is 1. So I've met the first requirement, which is those two must be greater than 0. Next, I'm going to evaluate the limit. So I'm going to evaluate the limit as n approaches infinity of a sub n over b sub n. So I have 2n plus 1 over n plus 1 squared all over 1 over n. Now I'm going to simplify that and evaluate my limit. So when I flip and multiply, I now have 2n squared plus n on the top, and I can either multiply out the bottom or leave it as is. I went ahead and multiplied that out. And from here, what I need to do is I need to evaluate this limit. Some of you from pre-calculus can recognize this limit, and if you don't, then we do L'Hopital's. So this is approaching infinity over infinity, so I need to do a L'Hopital's rule. And that gives me 4n plus 1 over 2n plus 2, which again approaches infinity over infinity, so I have another L'Hopital's rule. And I have 4 over 2, which is 2. So now I have a constant. I evaluated this limit and I got a constant. Let me run back up here. So I have situation number 1. I have a constant. Constant is greater than 0, less than infinity. That means that the sum of A and the sum of B both do the same thing. They either both converge or both diverge. So now I need to state what I know. Therefore, this sum that I'm asked about diverges by, and the name of our test, limit comparison test, and I'm going to have to erase this momentarily so I have space for my other problem, because this sum from 1 to infinity of 1 over n diverges. Okay, so next one, let's look at B. So for B, I have 1 over 2 to the n minus 1, and I need to compare it to something. Now, in this case, I can compare it to 1 over n if I want to, but I feel like, let's look at these terms. If I plug in 1, I get 1 over 2 minus 1, which is 1. If I plug in 2, I get 1 over 4 minus 1, which is 3. Plug in 3, I get 1 over 8 minus 1, which is 7. So I feel like these are going down significantly, which makes me feel like this one might converge. So what I'm going to compare this to is I'm going to use b sub n is going to be 1 over n squared, which I know is a p-series. 2 is greater than or equal to 1, which means, sorry, it's greater than 1, which means this thing is going to converge. So let's go ahead and evaluate this limit. So again, I'm kind of looking and going, well, do I think it's going to converge? Do I think it's not going to converge, to decide what to compare it to? So I have 1 over 2 to the n minus 1 divided by 1 over n squared. And this limit is going to be n squared over 2 to the n minus 1. I plug in n is infinity. And when I do that, I get infinity over infinity. That's infinity, which means I use L'Hopital's. So now I have the limit as n approaches infinity of 2n over the derivative of 2 to the n is, do we remember? 2 to the n times natural log of 2. And this one, I can do another L'Hopital's. I can say, that's approaching infinity over infinity. Do L'Hopital's again. Limit as n approaches infinity of 2 over this derivative is 2 to the n times natural log of 2 times natural log of 2, which is this. And when I evaluate this limit as n approaches infinity, I get 0. So I'm going to scroll back up now to look at my test. I got that my limit was equal to 0. So I have this situation right here. So I know that if b sub n converges, which mine does, that means a sub n converges. So by limit comparison test, my summation that I was evaluating is going to converge because the sum of the one I compared it to, which is 1 over n squared, converges. Now we need to say why. It's a p-series, and p is greater than 1. So that is example B. Moving on to example C. And again, I'm going to have to erase some stuff that I already have there, so I apologize. I'm going to clear this little space out. And let's talk about C. So C, I have this thing, and basically, again, if I'm going to look at this one, I have on top, my exponent is really just an n to the 1. On the bottom, my highest exponent is n cubed. So a good thing to compare it to would be 1 over n squared. So I'm going to go ahead and use 1 over n squared to compare this one. So just like I was doing with my last test, the direct comparison test, I'm just looking at the exponents. So for this one, I'm going to have the limit as n approaches infinity of 3n plus 2 over n cubed minus 2n all over 1 over n squared. So that limit, simplifying that, I have 3n cubed plus 2n squared all over n cubed minus 2n. Again, if you remember from functions trig or functions analyt, what happens to that, your pre-calc class, you may use that rule. Or I use L'Hopital's that approaches infinity over infinity, so I keep on going and I get 3 times 3 is 9 today. Okay, I get 9n squared plus 4n over 3n squared minus 2. And again, that approaches infinity over infinity. I do another L'Hopital's, and I get 18n plus 4 over 6n. And that again is infinity over infinity. I use L'Hopital's. And then the limit as n approaches infinity of 18 over 6, which is equal to 3. So I actually get a value. I'm scrolling back up to look at the test. So I got a value. I got this one, which means both of these series either diverge or converge. So I compared this one to 1 over n squared. So I need to do some writing here. I'm going to end up erasing this, so write down as I go because I'm going to run into my space for D. So therefore, the series that I was asked about converges by the limit comparison test because what I compared it to, which is 1 over n squared, converges, and that's a p-series. T is greater than 1. So last one we have is D, which is sine of 1 over n. Now that one's icky looking. So, but what I'm going to try and compare it to is I'm going to compare with 1 over n. That's what I'm going to compare it with. So I need to know actually a little calculus rule. So I'm going to have my limit as n approaches infinity of sine of 1 over n over 1 over n. And the little calculus rule that I need to remember is this one. We haven't seen it in quite a while, but we knew it at one time. Sine of x over x as x approaches infinity. Sorry, I wrote an n. Is equal to 1. And that's just a rule that we're supposed to remember, and I'm not sure that we do. A little refresher. So instead of having an x in my green limit, I have a 1 over n. But I have the same thing on the top, right here by the star, as I do on the bottom. And that's the point, which means this limit is equal to 1. So now I can go up to my test again. I have my limit is equal to a c. So again, I'm on number 1. My c is between 0 and infinity, which means these two things both converge or both diverge. So, therefore, by the limit comparison test, the series that I was asked about is going to diverge because the series I compared it to diverges. And we can just say it's the harmonic series, or we can talk about a p-series where p is less than or equal to 1. So there we have all of our tests. So in class what we'll be doing is using all of our tests to evaluate the endpoints of our open intervals of convergence. Please bring any questions that you have with you to class and have a wonderful evening.